Okay, so let's continue to the main points of the kinematic of mobile robots. So why do we need kinematics? Um, what can we do with the kinematic equation? Let's say, well, you have for omniwheel mobile robot, you have 4 actuator for the 4 wheels. So let's say you can control all the 4 motor. You can control velocity, or you can control position of the actuator. So what information from the velocity of the motor to the information of position or velocity of the robot itself. Okay, so giving the rotation angular velocity of let's call this phi 1, phi 2, phi 3, and phi 4. Phi dot. So these are angular velocity of the motor on the wheel. So how can we calculate or compute the velocity of the robot on the x-axis, hb dot, and velocity on the y-axis, b dot. So let's say if you choose a proper way that make the robot to move this way, this direction. So this vector has a component on, so this is velocity of the robot on the body frame. So it has component on the x-axis and it has component on the y-axis. So this is h dot b. So now I call this axis, and this should be h dot b. So I call this just axis, and then this component is y dot b. Okay. So from the information of phi dot to compute h dot. So phi here I mean phi 1 dot, phi 2 dot, phi 3 dot, and phi 4 dot. From here we compute h that has component h dot, y dot, and psi dot. So let's say you control the motor in a proper way so that the robot have the velocity vb, and at the same time it rotate by angles with the angular velocity psi dot. Okay, it move at the same time it rotate. Okay, so this one is called forward kinematic. Okay, then you think in another way. Okay, let's say I want the robot to perform some task. I want it to move from here to there with this velocity and with the angular velocity psi dot. Okay, so given h dot, capital H dot, and then you compute, okay, given h dot, then you compute phi dot, then we call this inverse kinematic. Okay, so kinematic, inverse kinematic are useful to generate a trajectory for the robot, and then send the desired value, the command, to control the motor so that the motor can rotate properly, so that we can have the robot move along the path that we want. Okay. So in this way, we say h dot equal to a function of phi dot forward kinematic, right? This one is inverse which means phi dot equal to f inverse of h dot. And now I want you to note something. It is very helpful for you to come up with how you can start looking for forward kinematic or backward kinematics. Um, because you for the introduction robotic part 1 you have learned robot arm already, so I put together for you to have some insight on the forward kinematic and inverse kinematic. So for robot arm, for the you can start with forward kinematics, right? You use geometric approach or algebraic approach to find forward kinematics for position first. This is the first thing you can do, you can find. Then you just take time derivative to find velocity equation. Okay. So forward kinematic first. Then taking second time derivative for acceleration equation, right? And for inverse kinematic, you can find for the position equation first, right? And you may also need to use forward kinematic equation, okay? Or you may directly find it from the geometry if some simple robot that does not need the algebraic approach to find inverse kinematic. And take time derivative to find velocity equation and acceleration equation. Okay, this is for robot arm. So it's very important to know the process so that you can start the right way from the right thing. How about mobile robot? What you can find first is the inverse kinematic for velocity. Okay, different from robot arm. You can find inverse kinematic for velocity equation first, and then you can take time derivative to find acceleration equation, and you can take integration of the velocity equation to have position equation. Okay. And then forward kinematics can be found using the equation 1 here. From the inverse kinematics, you can directly find forward kinematics. Okay. And then you take time derivative on the velocity equation to have acceleration equation. You can use equation 2 or you can use equation 4. Okay. And just do some manipulation of rotation matrix, and then you can have the equation that you want. And then forward kinematic for position can be found by integrating the equation 4. So this process is very important. You can organize your sort, and even you may be able to derive by yourself later on. So the next part is about rotation matrix also. The coordinate transformation from one frame to another frame using rotation matrices. Okay, now let's see. We already took a look at the body frame and global frame. But for the robot, it may have many parts, many components, many mechanisms. Then we need to attach all the frame, especially for omni wheel and mechanism wheel. The wheel itself has mechanism, have roller. Okay, and the configuration orientation of the wheel can be different. As you can see in this picture, okay, configuration of this type of wheels and this type of wheel. So first we need to choose the frame for all the wheel. Okay, now we already have body frame for the robot. Okay, the center of the robot is here, and then we attach a wheel frame. So this one is wheel frame, which is aligned with the motion of rotation. I would say, if you imagine the wheel is normal wheel, you imagine the direction of the wheel can have linear motion, right? Can transfer into linear motion. That direction is direction of wheel frame. Okay, the edge of wheel frame. This one I write it bigger. Wheel frame for the I wheel. I can be 1, 2, 3, 4 if you have 4 wheels. So then you have roller on the wheel. Roller can, if you push the force this way, roller can rotate freely, right? So roller is another component, another body. Then you attach another frame on the roller like this, and it denoted by HR of the wheel I. Okay. Now let's take a look at the angle that are denoted for distinguish the orientation of one frame with respect to another frame. So you already have psi is the angle between body frame and global frame, and you have alpha. Alpha is the angle of a vector from origin to the center of the wheel. Okay, this vector from the center of the robot to the center of the wheel, you have a vector, and that vector has angle with respect to the x-axis of the body of the robot. And then you have angle delta. You cannot see delta in here. Delta on this mechanism wheel. Delta is the angle between edge of wheel frame with respect to edge of body frame. So for mechanism wheel, delta equal to 0. Okay, delta I, all delta actually, not just delta I, because you see all the wheel, all the mechanism wheel, its frame. Okay, so this one is edge wheel 2, aligned with the axis of body frame. So delta is 0. How about gamma? What is angle gamma? Gamma is the angle between axis of roller with respect to the edge wheel. Is gamma. So for mechanism wheel, gamma is like this. Can be 45 degree or minus 45 degree, like that. Okay. So this is gamma. So for mechanism wheel, gamma must be different from 0. Must not 0. This is mechanism. Right? How about omni wheel? For omni wheel, let's take a look at the axis of the wheel and the roller. So we have HB here, and then H wheel here, H wheel. So delta, which is the angle between H wheel and HB, must not 0. Okay, different from 0 for omni wheel. How about axis of roller? So roller axis is this way, should be parallel, right? So axis of the wheel and then axis of roller parallel. So gamma equal to 0. Okay. And so it's very important to know how we can transform coordinate from one frame to another. Let's say I want to transform coordinate from roller frame to wheel frame. I can apply rotation matrix or WR of gamma angle. Okay, because roller has angle with respect to each wheel by gamma. So transformation coordinate of the coordinate from roller frame to wheel frame just use rotation matrix with gamma angle. And if you want to transform coordinate from the wheel frame to the body frame, you use rotation matrix with angle delta. Okay. And what if you want to transform coordinate from the roller frame to the body frame? Okay, if you want to transform like this, then you just apply rotation matrix of delta plus gamma. Okay. And what about if you want to transform the body, the coordinate from the body frame to the roller frame? What do you do? What rotation matrix you use? Subun? I don't know. Adrian? If we have coordinate on the body frame and we want to transform into the roller frame, what rotation matrix we use? Maybe yeah, that's my fault. I haven't explained before, right? So just use all transpose, right? Because all transpose is the inverse of the R itself. Yeah. Um, so if okay, I can explain another way or uh,
It's okay. We just introduce the question. But it's okay.
yeah, yeah. So but it also a nice way to see or what R transpose look like, right? Um, before yeah we have, let's say we rotate one frame with respect to another h1 this one y, this one y1. If we rotate by psi, r is cosine psi, sine psi minus sine psi, cosine psi, and r transpose would be cos psi here and sine psi here minus sine psi here, cosine psi here, right? And can I say this one actually cosine of minus psi? This one is minus sine of minus psi. This one is uh, sine of minus psi, and this one is cosine of minus psi. Can I say like this? Anyone? This and this are the same. This one and this one are the same. Cosine minus phi is equal to cos psi, and sine minus psi is minus sine psi, but the minus become plus, right? So, but for this one, you can say, oh, this one is just rotation matrix of minus psi, right? So what I'm trying to say here, rotation or transpose is the same as you rotate axis in a different direction. And okay, next should be uh, okay. So now you know how to transform the coordinate from one frame to another. Um, then we can start finding inverse kinematic. So what is the main idea that we can come up to find kinematics? So the idea is that for all the wheel, or actually all type of wheel, you have roller or non-roller on the wheel. The key is at any time there must be contact between roller and the floor. Anytime, right? There must be contact. And you imagine like this way that imagine that the roller can the wheel has infinite roller. Anytime it rotates, there is always a point touch on the floor. Imagine that way. Otherwise, you cannot come up with the right idea to derive the equation, right? Um, so at that point, that touch on the floor must have um, certain velocity, right? When robot move a certain velocity. If the robot move in the translate, that point also have translation motion. But if robot rotate, okay, so in with respect to the origin of the robot, that point also rotate. Okay, so inverse kinematics can be derived by starting from look at the velocity of point P, velocity of point P of the point at contact to the floor equal to velocity of the velocity of the origin here v of vector no of point OB, okay, velocity of point OB, and plus the velocity that this point P rotate with respect to the origin, okay, and it is actually omega cross vector from OB to P, OB to P, okay. If I because this one has two letter, I should put a vector on top. Easy. Okay, let's put all vector. Okay, like this. Okay, all of these are measured in the global frame, right? Always true. Okay, this relationship is always true, and then okay. Well, here the information of velocity on the point P with respect to global frame. And but what I can know is that the wheel can have velocity from the motor, right? From the motor, and the information can be found on the roller frame. On the roller frame, if we use the information of the angular velocity of the actuator of the motor. Okay, so velocity of the roller itself is on the roller frame. So we must transform this one into roller frame, right? But first transform it into body frame. Okay, transform this to body frame. To body frame. So I rewrite this in the algebraic form. Vp equal to VOB plus omega cross. I just denote this by SP. SP is this vector and measure in global frame. Then transform into body frame. Okay, from here. how can I, what can I do to transform into body frame? Adrian? Now I have this relationship in global frame, but I want to transform into body frame. Yeah, rotation symmetry with what angle? Yeah, so I apply rotation symmetry transpose of what angle? Psi, right? Because psi is the angle that represent the body frame rotate from global frame. So here I think maybe it's not enough to write here. Yes, I just say I apply rotation matrix to this equation. So I rewrite here. So R transpose psi apply on VP equal to R transpose apply on VOB plus R transpose apply on omega cross SP. Okay. Then what I have here is VP on the body frame. Okay. And here VOB on the body frame. So what does this mean? Yeah, many students get confused with this. They always say, "Oh, velocity of the point O B here is zero on the body frame." Actually, no. The position itself, the position of OB with respect to frame HB, YB is zero. That's true. But velocity, because any point have velocity, and velocity can be to any direction. It has component, and this component can be measured on global axis or can be measured on body frame, right? Always. So not zero. Okay. So then I apply this one rotation matrix to the omega and cross rotation matrix transpose to the S this vector before we measure on global frame, but now we apply this rotation matrix to transform into body frame, right? So I can write here this one like VBOB plus this one. Okay, what happened with omega? We have omega equal to 0, 0 omega z, rotation only on one axis, z. And if we apply rotation matrix, is it still the same? Okay. Now I have cos psi, sin psi, 0, 0. Oh, sorry, minus sin psi, cosine psi, 0, 0, 0, 1, and apply on the angular velocity 0, 0, omega z. What do I get? Still 0, 0, omega z, right? So here is still omega cross. This one become S on the body frame. Okay, where S on the body frame equal to what? If you know this length is L, actually for the robot you construct by yourself, you design by yourself, you know this length, you know this distance B, you know this A, and you choose this one is as L square root of A square plus B square. So you know this L, and then you can have this one is just L cosine alpha and L sine alpha. If I want to write three components, so L sine alpha and 0, right? For this S. SP here is on on this frame, but SP on B frame here, this one, right? So S here, be careful, S here, it has SP and it has SP on B frame. The same vector but can be measured in different frame. Okay, so now VP equal to V VOB here on body frame plus omega cross L cosine alpha, L sine alpha, and 0. Maybe I just keep S there. Okay. So what is V? Yeah, I should let you know now. This one. So velocity of point OB actually is the velocity of the robot itself. So if OB is has coordinate X and Y, so velocity at OB, velocity at OB actually is H dot Y dot, right? So okay, where VOB is actually H dot Y dot. No, not just H dot Y dot, but H dot Y dot and psi dot. I put this together. And what about um, VOB but on body frame? HB dot, YB dot, and psi B. Oh, psi no need, dot, like this. Okay, we will use this. And okay, so now transform into roller frame. To roller frame. Okay, so we apply rotation matrix of what angle? Rotation transpose of what angle? From body frame to roller frame. Số 4. From body frame, okay, here body frame to roller frame. Here this is roller frame. So from body frame to wheel frame we have angle delta, and then from wheel frame to roller frame we have angle gamma, right? So we apply rotation matrix of delta plus gamma to rotation matrix on omega cross SBP. Okay, then this one become H roller on roller frame now. So HP of roller frame dot, and this one is YP on roller frame, dot, and velocity because this one is 3 component. Yes, 3 component. So this one I should have no, I don't have velocity in here. 0 equal to this one. right? And time this one is h dot b y dot b psi dot, okay, and plus, and oh sorry, I think, yeah, should be like this, yeah. And then this one time this, because this rotation matrix apply to this omega. Oof, I think I should write like this first, yeah, and then cross, okay, like this. So this one is just uh, hb dot cosine delta plus gamma minus yb dot, minus sign is here, sorry, minus sign is here, so this one is plus sine delta plus gamma, okay. How about this one? Minus hb dot sine delta plus gamma, and here is plus y dot b cosine delta plus gamma, and this one just psi dot, okay. And then plus this one is still omega cross. How about this one? um, yeah, this one become omega cross, okay. This one become L cosine or sine, this one, maybe we need to find it first. Okay, let's write this down, delta plus gamma, and here minus sine delta plus gamma cosine delta plus gamma. Maybe write this one to be shorter, cos delta plus gamma minus sine delta plus gamma sine delta plus gamma cosine delta plus gamma 0 0 0 0 1, and this one is L cos alpha, L sine alpha, and okay, so cos time cos plus sine time sine, okay, cos plus sine sine, so become cosine of this angle minus this angle, okay. So the next page should be h dot p or frame equal to h dot b cosine delta plus gamma plus y dot p sine delta plus gamma and plus plus L, yeah, if I use this one 0 omega z root of psi dot, so I only have yeah, this one cut this time this. No. This one become a matrix. So the last row must be all zero, right? Yeah, okay. Okay, so here become L psi dot cosine delta plus gamma minus alpha and y r dot p equal to minus hb dot sine delta plus gamma plus y dot b cosine delta plus gamma, and this one sine cosine, oops, minus is minus before, so, okay. Okay, so this one is L psi dot sine delta plus gamma plus minus alpha. Okay, and yeah, here is the main point of the kinematics, inverse kinematics. Sorry. Um, so this part we can define velocity of point P on the roller frame. Yes, from the information of the robot motion. Okay, hb dot y h dot b y dot b and psi is the velocity, yeah, velocity of the robot, velocity of robot in one direction measured in body frame to the, okay, transform into the velocity of the roller on the wheel. Okay, roller on the wheel. And we can also have velocity from the wheel itself, from the roller itself, induced by the motor. Okay, so let me choose this picture in order to explain this one. Control C. So here, look at this wheel. Look at this roller, this wheel. So, sorry, not this one. Mechanism wheel. Choose mechanism wheel. This one. Okay, so because we have a motor with the axis like this, and the motor rotate the wheel. So let's say it rotate this direction, so it can push the wheel to move this direction, right? Supposed to push to this direction, right? Yeah, but because the roller can rotate freely in this with respect to this axis, the HR, it means there's no force that can push robot in this direction, right? There only force that push robot in this direction, right? Correct? So assume that the roller has no slippery on the floor. It means um, the force that pulls the robot in this way such that the velocity of uh, okay, so the velocity on this axis contributed by the velocity of the motor go all this way, right? I mean, so originally velocity on the wheel, if it's not more wheel, velocity is this direction, this component. But because only the velocity on this direction that can produce the movement, so um, we project this velocity to this axis. So we have, okay, what is the velocity on the direction? So it is phi dot times the radius of the roller, of the wheel. This radius of the wheel, right? Radius of the wheel. So this is the tangent velocity on the wheel. And so if we project on this axis, H dot R contributed by the motor angular velocity equal to phi dot times roller and time cosine gamma. Okay, because this segment is one of the right triangle, right? Is okay. One edge of the right triangle, and this one must equal to this. Okay, so we have H dot P R equal to H dot R that contributed by the motor. Okay, then we can have let me write this one first. Okay, then we can have phi dot times R times cosine gamma equal to HB dot cos delta plus gamma plus y dot b sine delta plus gamma plus L phi dot cosine delta plus gamma minus alpha. Okay, and then we can write phi dot equal to 1 over R cosine gamma times cosine delta plus gamma. I write like this. and time h dot b, y dot b, psi dot, no, this one, okay. And then if we say this is for wheel I can put I here, put I here, or also or I here for wheel I, Li. Okay. So this is the relationship between angular velocity of one wheel I to the velocity of the robot. So then we have 4 wheels, then you take I from 1 to 4. Okay. So take I from 1 to 4. Then we have phi 1 dot equal to, I just call this J11, J21, J31, 1 2, 1 2 1 3, and time h dot b, y dot b, psi dot, and then phi dot phi 4 dot equal to J41, J42, J43 time the same thing. Okay, so finally I have a complete equation for the inverse kinematic just like this. Okay, and J here is 4 by 3. Any question so far? So Bun? No question? Yeah, finally we have very simple equation, right? And J is constant actually. Oh, I should put B here. Yeah, because B in the body frame. Okay, the thing is, if we have 3 wheels, it's easy. If we have only 3 wheels, for example, omni wheel, so phi dot equal to J3 by 3 times HB dot, then forward kinematic would be H dot B equal to J inverse times phi dot. But for this one, if I want to find H dot B, what can I have here? Time for here. Because we have, yeah, so it's, so why it happened like this? You imagine if you have 3 wheels, 3 wheels can contact on the floor as a form, as a plane, right? 3 wheel, 3, we can say, okay, 3 input and 3 output. Oh, I mean input like velocity of the wheel, and then velocity of the robot on x, on y, and rotation. Okay, so it's like you have three unknown, three equation. So that's why. But now, so three wheel is okay to determine velocity, x, y, and rotation. But if you have another wheel, if the fourth wheel rotates not properly, it just fight with other. You got the point?
So you just reduce one.
So if the fourth wheel is controlled properly, it rotates properly, it can help other. So it's like if you have three unknown but four equation, the three equation have solution. But if that solution does not satisfy the fourth equation, it means you don't have solution. But if the solution also satisfy the fourth equation, it means yeah, we have solution. So it's the same thing as if the fourth wheel rotate properly, have velocity properly, then we have solution.
So we put these brackets.
So let's say if you just control velocity without thinking about kinematics, you know all the phi, phi.1, phi.2, phi.3, phi.4, and then you want to calculate where the robot go, right? You don't have the solution, but you can have the best answer. What does it mean? It's like I illustrate in like this. If I give you three points and ask you to find a line that fit all the 3 points, it's not possible if they are not in the same line, right? But if I say, can you find the line that almost pass all the three, that the arrow from one point to the line, okay, you have E1, arrow 1, arrow 2, arrow 3. If you can find a line that can minimize the error, then I can say it's the best line. You can minimize this. Okay, I can say it's the best line, the best answer. And same for this one. If you know the information of angular velocity, please find the best answer that where the robot will move, how it will move. And the best answer is using the least square method. Least square of a tall matrix will be yeah, actually you can find like by like this. You multiply J transpose here and then J transpose here, then you can have inverse of this one. So J transpose, J here, inverse, and then you can have this one, J transpose. Oops. Okay. And this one is called least square. Least square solution. Least square method. I mean the best inverse of J. It's not exactly the inverse, but the best inverse. Right? Okay, so that's all for today.